In section 7, we will learn about how to use autoencoders to colorize images. Introduction to autoencoders. But what exactly is an autoencoder? An autoencoder neural network is an unsupervised machine learning algorithm that applies backpropagation, setting the target values to be equal to the inputs. An autoencoder is trained to attempt to copy its input to its output. Internally, it has a hidden layer that describes a code used to represent the input. So in another sense, autoencoding is a data compression algorithm where the compression and decompression functions are data-specific, lossy, and learned automatically from the examples rather than engineered by a human. Additionally, in almost all contexts where the term autoencoder is used, the compression and decompression functions are implemented with neural networks. So how does an autoencoder work? So autoencoders are unsupervised learning technique in which we leverage neural networks for the task of representation learning. Specifically, we'll design a neural network architecture such that we'll impose a bottleneck in the network which forces a compressed knowledge representation of the original input. If the input features were each independent of one another, this compression and subsequent reconstruction would be a very difficult task. However, if some sort of structure exists in the data, this structure can be learned and consequently leveraged when forcing the input through the network's bottleneck. So to summarize, an autoencoder is trained to attempt to copy its input to its output. Internally, it has a hidden layer that describes a code which is used to represent the input. Once we have a hidden layer that describes a code, we can then reconstruct the output from this code. So code and latent space representation are being used interchangeably in this context. So this is a diagram of how a simple autoencoder looks like. We have an input x, and then we have a code z, and then we have an output x dash. As you can observe from the diagram that x is our original input and z is the latent space representation of our input called code, and x dash is the output that is reconstructed from our code z. Also in the diagram you can notice that there is a concept of encoder and decoder. So what exactly is this encoder and decoder? So the network is trained to reconstruct its input, which forces the hidden layer to try to learn good representation of the inputs. So this type of network has two parts, encoder and decoder, as we already discussed. So encoder is a part of a network that compresses the input into a latent space representation or code. It can be represented by an encoding function z equal to f of x. So decoder is a part that aims to reconstruct the input from the latent space representation or code. It can be represented by a decoding function x dash equal to g of z. So the autoencoder as a whole can thus be described by the function g of fx equal to x dash, where we want x dash as close as the original input x. So in mathematical terms, this was the definition of autoencoder. So if the only purpose of autoencoders was to copy the input to the output, they would be useless. Indeed, we hope that by training the autoencoder to copy the input to the output, the latent representation will take on useful properties. This can be achieved by creating constraints on the copying task. One way to obtain useful features from the autoencoder is to constrain code of z to have smaller dimension than x. So in this case, the autoencoder is called undercomplete. If x dash has a higher dimension than that of z, then the autoencoder is called overcomplete. So we'll talk more about the undercomplete autoencoder, which is one of the types of autoencoder. So the simplest architecture for constructing an autoencoder is to constrain the number of nodes present in the hidden layers of the network, hence limiting the amount of information that can flow through the network. By penalizing the network according to the reconstruction error, our model can learn the most important attributes of the input data and how to best reconstruct the original input from an encoded state. Ideally, this encoding will learn and describe latent attributes of the input data. Because neural networks are capable of learning non-linear relationships, this can be thought of a more powerful generalization of PCA. whereas PCA attempts to discover a lower dimensional hyperplane which describes the original data. Autoencoders are capable of learning nonlinear manifolds. So another type of autoencoders is sparse autoencoders. So sparse autoencoders offer us an alternative method for introducing an information bottleneck without requiring a reduction in the number of nodes at our hidden layers. Rather, we construct our loss function such that we'll penalize activations within a layer. For any given observation, we'll encourage our network to learn an encoding and decoding which only relies on activating a small number of neurons. It is worth noting that this is a different type of approach, as we normally regularize the weights of a network and not the activations. So this was all about autoencoders.